What's up, everybody? How's it going? In this video, I'm going to attempt to speedrun through 3 coding interview problems of progressively increasing difficulty. I'm going to start with an easy problem, then move on to a medium one, and finally go to a hard one. These are 3 of the free coding interview problems that we have on AlgoExpert, and the interesting thing about this attempt that I'm doing is that, on the one hand, these are 3 problems that I wrote and I made the video explanations for on AlgoExpert, so I'm familiar with the problems, I've done them in the past, but conversely, these are problems that I haven't even touched in years. I think one of them is from the very first batch of problems on AlgoExpert, so 5.5 years ago. The other 2, I think, are from about 3 years ago, and I haven't prepped for coding interviews in 3+ years. I haven't really done things related to algorithms and data structures in at least a year or so, a little bit more, and I haven't really been coding for the last few months. So I definitely feel very rusty, very washed up. I'm still feeling relatively confident. I promise that I haven't looked at the problems recently, so I'm going to be rediscovering them with you in this video. And so yeah, I'm excited to see how I do. So with that, let's jump straight into the problems. But I guess first, platinum blonde hair, what do you think? Yay, nay? Let me know in the comments below. But so okay, let's jump into the problems. So I have all 3 of them here open in different tabs. We're going to start with the easy problem, validate subsequence. By the way, if you're a software engineer preparing for your technical interviews, do check out my company AlgoExpert. Go to algoexpert.io, use the promo code CLEM, C-L-E-M, for a discount on the platform. And so let's begin. I'm going to start the stopwatch, and we're going to time myself for the 3 problems. So ready, set, go. Validate subsequence. Given 2 non-empty arrays of integers, so they're non-empty and only integers, write a function that determines whether the second array is a subsequence of the first one. A subsequence of an array is a set of numbers that aren't necessarily adjacent, so they don't need to be next to each other, but that are in the same order as they appear in the array. So for instance, 1, 3, 4, they are a subsequence of the array 1, 2, 3, 4 because, yeah, they're in the same order, but they're not necessarily adjacent, 1 and 3 aren't adjacent here. And so do the numbers 2 and 4. Yeah, 2 and 4. So note that a single number in an array and the array itself are both valid subsequences of the array. Okay, so I think I understand. I see the sample input. Let's try to jump into the problem. By the way, I'm going to do this in JavaScript because this is the language I feel the most comfortable in right now. Should be pretty easy to follow. But yeah, so let me make the code full screen. So okay, how are we going to solve this? I think that we are going to keep track of 2 pointers, or rather 1 pointer in the sequence array, and then we are going to iterate through the array, the main array. We're going to see if the element at the index in the sequence is matching, and if it does, then we just move the pointer in the sequence to the right until we reach the end of the sequence. And if we ever reach the end of the array without having reached the end of the sequence, I think that's when we return false or something. So let's try this. We're going to say const, or rather let, because we need to be able to update this variable. In JavaScript, const means you cannot update it. Let sequence idx equals 0. And then we're going to say for const value or number of array. So we're iterating through the numbers in the array. Const number of array or we can say const sequence, or let's just say if number equals to sequence at index sequence idx, then we have a match. Then we are going to increase sequence idx, so we're going to say sequence idx plus plus. And then that's it, right? And then we can say, in other words, we're done with the check. But here, what we can do is we can say if we are at the end of the sequence, return true. So if sequence idx after this plus plus, after this update, is greater than sequence dot length, or is equal to sequence dot length rather, right? Equal to sequence dot length. So we are after the end of the sequence array. Then we return true, because that means that the sequence was indeed a subsequence in the array. If it's not there, we don't do anything because, like, we have to keep going. We have to continue iterating through the array. And I think that's it. And then we just return false here, because normally we will always hit true if we have a subsequence. So I think this is the solution. Let's just run through it once to see, I guess just for fun. So, okay, this one took me only 3 minutes and 30 seconds so far. But for fun, let's not pause the timer, act as if this were a real interview where I'm going through some test cases. So we have the sequence IDX starts at 0. We iterate through all the numbers of our array, right? We start from left to right. If at a given number, that number is equal to the number or the value in our sequence at the current sequence IDX, then we have found a number in the sequence that is like part of a subsequence in the array. So we can move on to the next number in the sequence. So we do sequence IDX plus plus. You increment it by 1. This is the same thing as doing plus equal 1. And then right after we say, okay, well, if our new sequence IDX is equal to sequence.length, then we return true, right? Otherwise, we return false. Or otherwise, if we get out of the for loop. And yeah, then we'll just, if this is not equal to true, so we still have more numbers in the sequence, we just get to the next number in the array, and that's that. So I think this works. The only thing we said, they're non-empty. Oh, they're non-empty arrays. So non-empty, so we don't need to handle some weird thing like if they're both empty, return true. So okay, I genuinely think this is going to work. Let's see. Let's run code. I guess I'm just going to submit code immediately. Boom, it worked. Okay, awesome. So problem number 1 done. That was 3 minutes, 30 seconds, just like pure coding, and then about 5 minutes, or 5 minutes, 10 seconds with the timer, with the walking through test cases. Okay, feeling good. Let's move on to the second problem. So river sizes. Let's start the timer now, or the stopwatch. 1, 2, 3, go. So this, I think, is like the oldest problem, one of the very first problems I ever did on AlgoExpert. You're given a 2-dimensional array, a matrix of potentially unequal height and width, so not necessarily a square, containing only zeros and ones. Each 0 represents land, and each 1 represents part of a river. So a river consists of any number of ones that are either horizontally or vertically adjacent, but not diagonally adjacent. And the number of adjacent ones forming a river determine its size. Note that a river can twist. In other words, it doesn't have to be a straight vertical line or straight horizontal line. It can be an L shape, okay? Write a function that returns an array of the sizes of all the rivers represented in the input matrix. The sizes don't need to be in any particular order. Okay, that last sentence is really important because that just makes things easier. Okay, so here you can see we've got a sample input. This is a matrix. We've got a bunch of 1s and 0s. So let's see. 2 adjacent 1s, that's 1 river of size 2. Here, this 1 is adjacent diagonally, but I think they said, or I said, diagonally doesn't matter. Yeah, but not diagonally adjacent. So size 1. Then here, another 2. So that's size 2. Then 1, 2, 3, 4, 5. Size 5. And then 2. So I think we've got 1 size 1, 3 size 2, 1 size 5. Yeah, 1, 2, 2, 2, 5. Okay, we're not told if this is like potentially an empty 2-dimensional array. Let's see if that matters, or if they're, empty like columns or rows or things like that. We know that it only contains 0s and 1s, and it's potentially a rectangle. Okay, sounds simple enough. So I'm going to full screen the code. By the way, it took like 2 minutes to just read the prompt. But so, okay. So here, this is going to be like classic, graph problem. By the way, I completely forgot for the validate subsequence. Okay, let me just quickly pause. Pause, go back to validate subsequence, restart the timer. space-time complexity. So this is going to run in O of n, where n is the length of the array, which is always going to be, I think, bigger than the subsequence. But yeah, it's O of n length of the array, because we'd never iterate through the sequence. And these are all constant time operations, so let's double check. Optimal space-time, O of n, and zero space. Or constant space, length of the array. Okay, I'm so washed up, I forgot that that's part of an interview. Time and space complexity. Okay, so 5 minutes, 48 seconds. Okay, river sizes. So this is going to be a classic graph traversal problem. We're going to iterate through the entire matrix. Whenever we see ones or a 1, we are going to start doing a depth first search or breadth first search. Doesn't really matter. We'll see how we implement it, where we just kind of, look at all the neighbors and we keep, or not diagonal, just horizontal and vertical, and we keep exploring them until we no longer find ones, and we keep track of the size, and that's that. And then we mark nodes as visited so that we never have to revisit them. And so I think that's going to be just an O of n times m algorithm, where n and m are the dimensions of the array, because we're literally just gonna visit each element once. That's it, or at most like twice when we iterate through the array. But this will be more clear as we type it out. So let us try to type it out. So we are going to do river sizes, takes in a matrix. So let's see, we want to go through I think we need to keep track of the rows and columns, like the indices, because we're going to need to access like neighboring indices. So we're going to do for let, so you iterate through what? Rows first, right? The length of a matrix is row. So for let row equals 0, row less than matrix dot length, row plus plus. That's how you iterate in JavaScript. Then we're going to do for let call equals 0, call less than or equal to matrix at row dot length, and call plus plus. The reason we do matrix at row dot length rather than like grabbing the length of the rows or whatever is because we were told this is like a potentially uneven matrix. So like, I'm not sure, I guess if like some rows can jut out more than others, but we know that it's like, it can be a rectangle for sure. So we're just going to do it like this. And then, so we have, row and column. And here this is where we want to do our sort of like, depth first search or breadth first search. Now, we do not want to revisit, we don't want to do like a breadth first search if something has already been visited. I suppose we could put that check in our recursive function, because I'm going to do this recursively. So yeah, I'm not going to worry about anything here. I'm just going to say, we're going to call our recursive algorithm. So I'm going to call this like traverse through river. And so this is going to take in the matrix, the row, and the column. Okay. And so here, this is where we are going to need our visited matrix, like or object or map or whatever, that's going to keep track of whether we've already visited these nodes. I'm going to make this just a matrix that's going to be same exact like space as this matrix. So we'll do const visited matrix equals, and so we just basically need to copy this matrix, like the dimensions of this matrix, and just make everything be false at first, and we're going to flip them to true whenever we visited a node or a cell in the matrix. So excuse me, in JavaScript, to copy a two-dimensional array, let's see, how are we going to do this? We're going to say matrix dot map, so you're mapping each row. So row to row dot map column, and so we map everything to false with a small f. So I think this creates our matrix. Pretty sure this is like the initial matrix. Okay, so traverse the river. we need to pass in the visited matrix. So let's pass in the visited matrix. And then we're also going to need to pass in something where we're going to store like the river sizes. So I guess I'll just write that already. We'll say const sizes, because the function is called river sizes. So sizes equals an array. The question said an array, right? Yeah, return an array in no particular order, okay? So sizes here, we're going to add sizes at the end, and this is where we are going to push values of rivers to that. And so I guess at the end, we're just going to do return sizes, and that's it, right? That's it. So function traverse through river, right? Traverse through river takes in, let's just copy paste all of this. It takes in a matrix, row, blah, blah, okay? So what do we do? First thing first, we say, if the cell has already been visited, like the node that we're at, we skip. So we say if visited matrix at index row call is equal to true, so we can just say if it's truthy, then return. Let's just return. Otherwise, we set it to true. So we set it as visited. So visited matrix row call equals true. Okay. Then, if this is a 0 in the matrix, right? If the value is 0, wait, was it 0 or 1? That's a river. So 0 represents land, 1 represents river. We care about river. So if it's a 0, we also return. So if matrix row call equals 0, return, okay? And so now we are dealing with a 1. And so what do we want to do? We want to increment some value, right? We want to increment some value. So we will never revisit visited nodes, so we don't need to worry about like doubly incrementing, counting the same node. Okay. But let's see, how do we keep track of the size? So the size at any given point would be, I think, let's see, where would we want to push the final size to the sizes array? Like, we can't push it if it's a 1. Maybe we want to push at the top, so here. Okay, like, so one way that we could do this, the way that comes to my mind, the quickest right now, but which is not like my favorite, is I'm gonna have like an object that can mutate, and that I'm gonna instantiate here. So I'm gonna do like let current river size equals an object that says current river, or just value 0. Okay. And so I'm going to pass in current river size here. And then at the end, like right after, I'm going to say if current river size dot value greater than 0, so if we got a river, then we're going to do sizes dot push current river size dot value. Okay. Otherwise, don't do anything, and then return sizes. Okay. Now, I don't know, like, I'm not a fan of like passing in an object where we mutate the value every time, but let's just do that for now. So current river size, we're going to put this here. So then here it would be, we know that we are dealing with a 1. So we're going to do current river size dot value plus plus. So we increment the value, and this increments it for every other node in the same sort of like depth first search. And then we have to call this function, like the traverse through river, for every neighbor of our current node. So neighbors are going to be, left, right, up, bottom because they are it's not diagonal, and because we have to deal with edges of the array where we can get out of bounds, I'm going to make a function to get the neighbors, and then we're going to call it. So we're going to say const neighbors equals get neighbors, and here it's going to be literally matrix row column. And then we're going to say for const neighbor of neighbors. This is your classic, depth first search. Const neighbor of neighbors, traverse through river matrix. So the neighbor we're probably going to want it to be like tuples or like arrays of length 2 of the neighboring row and column values. So here I'm actually going to destructure this row call. So for const row call of neighbors, again to be clear, like the neighbors array is going to look something like this, like 1, 2, 0, 1, where 1 and 0 are rows, 2 and 1 are columns, and like these arrays of length 2 are individual neighbors. And so here I'm grabbing immediately row and call for each neighbor. This is just like JavaScript destructuring notation. And so I'm going to pass, and I guess I should call this neighbor row, neighbor row, neighbor call, so that we don't have collisions with these two variables. And so I'm going to pass in neighbor row, neighbor call, visited matrix, current river size. Okay? Current river size. And that's that. Now we just need to write the get neighbors function, and I think we're done. So function get neighbors. This is kind of like the annoying function. I always say this in AlgoExpert video explanations. Like, this is where in an interview I would ask the interviewer, like, do you want me to write this? Because it's really just like edge case checking. But here we're going to do it. So we're going to say if row equals or not equal to 0, right? If we're not equal to 0, then there's a value to our there's a value above us. So and I guess here I need to put neighbors. So const neighbors equals an empty array, right? And so if row not equal to 0, neighbors dot push row minus 1 column, so the value above us, right? Then if call not equal to 0, then neighbors dot push row, the same row, but call minus 1. That's the value to the left. Then if row not equal to, so let's see, we don't want to be the last value. So matrix dot length minus 1, right? If we're not the very last value, then we do neighbors dot push row plus 1 call. And then finally, if call not equal to, so what's the value, the last value of the columns? So this is where I guess earlier when I was saying like, can the matrix be like jagged where some rows like jut out? I don't think it can be. I think the matrix has to be like rectangular, right? Potentially unequal height and width. So here we would have to double check with our interviewer, but I'm like 90% sure that, or 99% sure it has to be like rectangular or square. But so rectangular, this is going to be, matrix dot length, or no, matrix at index 0, right, at any row, dot length minus 1, neighbors dot push, row call plus 1, okay? So now return neighbors. Okay, so I think this works. Let's walk through it once and then run the code. Just so that we see, I'm at 15 minutes and 45 seconds without having, re-walked through it. So if we're in a competition, I would like immediately press submit. But let's see. So we've got our main river sizes function, takes in a matrix. We first instantiate a sizes array. So we are going to have then a visited matrix, which is matrix.map. So we're mapping every row to a map of that row where every column is equal to false. Okay, because nothing is visited at the beginning. Then we iterate through all the rows, right? So row less than matrix.length to go to the very last row. Then every column in that row, okay, the current river size, starting at that index, is this object with value 0. Then we traverse through the river, passing in our matrix, row and col, visited matrix, current river size. And at the end of this depth first search traversal, if the current river size.value is greater than 0, then we have found a river. And so we push to the sizes, current river size.value. Otherwise, if it's still equal to 0, just don't push anything. And at the end, we return sizes. So here, we are iterating through every value in the matrix. So this is going to be an O of n times m function. This function is O of n times m. We'll see like what the other ones if they mess it up, but O of n times m, where n is the, let's say, width, and m is the height. Or if you want, you could say like O of, big N, where big N is the total number of cells in the matrix. Okay, so that's this algorithm. Now, traverse through river, and the space is also the same thing because we've got this visited matrix. Now, traverse through river, the first thing we do is we say, hey, if we've already visited this value, then return. And that's good because like we might have a river like in the sample input, right, where we start at 1, top left, we will visit the one right below, right? And then when we continue iterating through the matrix, like at the top level, when we get to this bottom one here, we don't want to revisit that and redo the algorithm. So here we would return immediately. Okay, so return. Otherwise, we immediately visit that node. Then if the value in that matrix, or in the main matrix, is 0, then we don't need to update current river sizes or current river size or anything, so we return. And then we do current river size dot value plus plus. And so, yeah, in that top level, top river in the corner, we would immediately increment. It would be 1. And then we grab all the neighbors, get neighbors of our current matrix, row, and col, for const neighbor row, neighbor col of neighbors. So we get the neighboring row and column of every neighbor. And we immediately call this method. And for any neighbor that we've visited already, we return. And otherwise, we do the same exact thing, increment the river size value, blah, blah. And so here, you can imagine that, like, because we are using this visited, this visited matrix, we're at most going to visit any node twice. I don't think we will ever visit a node more than 2 times. Or maybe, I guess, some of them we might visit like 3 or 4 times, if they're like neighbors of a node that we haven't visited, something like that. Yeah, that we might do. Like, imagine you had, let me keep writing here. Imagine you had an array where it's like, 0, 0, 0, then same thing. All right, let's keep doing that. Boom, boom. And here, imagine you've got like 1, 1, 1, and 1. Like at this one, we would visit the bottom neighbor. And then, or we would call traverse through river on the bottom neighbor, but it would immediately be visited, so we would return false. On this one, we would also traverse this one, but immediately return false. On this one, we would also visit this one, immediately return false. On this one, also visit this one, immediately return false. So the point is, like, this node will at most be visited 4 times, and most of them will not be visited 4 times. So, or I guess 5 times, because you also have to visit it like once when you're iterating at the top level. So yeah, at most, like grand maximum, you're bounded by like O of 5 n times m. So that doesn't change the complexity of the algorithm. And then get neighbors, create our array. If row is not equal to 0, then we've got a value above, so row minus 1 column. If column not equal to 0, we've got a value to the left, so row col minus 1. If row not equal to matrix.length minus 1, the last row, then row plus 1 col, we've got a value. Let me just double check, did I mess up my time? 21 minutes, 5 minutes, okay, we're good. Sorry, my camera stopped recording. Okay, so row plus 1 column, a value below us. And then finally, if col is not equal to the final column, so matrix 0 minus 1, then we push row and call +1. Okay, so I think this works. In an interview, I would basically be telling the interviewer that that I think this is good. So let's submit code. Let's see. Yes. Okay, it works. Okay, I'm happy. And so this took about 21 minutes and 50 seconds. So far I am at about 28 minutes. So let us now see the final question. So shift linked list. So this is the hard question. Let's start the stopwatch. Start. So shift linked list. So write a function that takes in the head of a singly linked list and an integer k, shifts the list in place, i.e. doesn't create a brand new list, so we can't create new nodes, by k position, and returns its new head. So what does it mean to shift a linked list? It means moving its nodes forward or backward and wrapping them around the list where appropriate. For example, shifting a linked list forward by 1 position would make its tail become the new head. Okay, I understand. Whether nodes are moved forward or backward is determined by whether k is positive or negative. Okay? And then each linked list node has an integer value as well as a next node pointing to the next node in the list, or to none null if it's the tail of the list. You can assume that the list is always going to have at least one node. And I'm assuming that in that case, shifting just doesn't do anything. Okay, so here we have a sample linked list. It goes from 1 to 5, or 0 to 5, and the head node with value 0, okay? K is equal to 2, so if you shifted by 2, 4 would become the new head, right? Yeah, 4 becomes the new head. Oh, and sorry, quick pause. The complexity analysis of river sizes, was I correct? O of n times m? Yeah, WH with height space. That's what I said. Okay, cool. So let's restart the timer. Okay, so here, 4 got shifted here. Okay, so I think this is, I understand the prompt. Let's see how we're going to do this. So full screen here. Shift linked list head and k. So we want to shift by k. My brain is blocking. Want to shift by k. So if we want to shift by 2, let's look at the example again. Shift by 2 here. We have to get the second node from the end, right? And then we take the node before it, make it point to null. That's easy. And then make its node point to the head. Okay. Let's see. But how do we count backwards from a linked list again? So if we shift by 2, first of all, by the way, if k is if k is greater than the total number of nodes in the linked list, we just mod, right? We just mod by that number. Like if here k were equal to 1, 2, 3, 4, 5, 6, 8, we would do 8 mod 6, that's equal to 2, and that would be the same thing. If k is negative, not entirely sure what we do. Okay, let's see. This is why this is a hard question. How do we shift a linked list? So, we have the head. Okay, so let's see. One way of doing this is you grab the length of the linked list, then you mod the number by the length, like k by the length, and then you count until you retraverse the linked list. You count until you are like 2 away, or whatever the resulting number is, away from the end. And you grab the pointers and you do that. Okay, let's try that, and then we'll see with negative numbers. I'm not sure how to handle negative numbers. Wait, did this say positive? No, an integer k, so it could be negative. Okay, so look, here's what we're going to do. We're going to get the length of the linked list, then mod k by the length, and then once we have the final result of k, and we have the length, here we have the length of 6, we're gonna jump 4 positions, 6 minus 2, the final value of k, so 1, 2, 3, 4, and we are gonna that's when we're gonna do the switch. Okay, so I think that makes sense. I'm not sure how we're gonna handle negative numbers. So let's start by calculating the length. So we're gonna say const length equals get ll length. Okay, or let's go get list length, taking in head. So this is going to be a pretty easy function. Get list length takes in head, and we say let current node equal head, let length equal 1, and we say while current node is not equal to null. So while current node isn't equal to null, we say length plus plus. So I should start at 0 here. Length plus plus, and then current node equals current node dot next. And that's it. And then we return the length. So this gets us the length of the linked list, and it's an O-then operation where n is the number of nodes. Now let's see. We have the length. So we say, I'm going to assume k is positive. Okay. If anything, actually, let's say like if k greater than 0, do something else. Do something else. Handle negatives. And I guess if k is equal to 0, we can just return head. So I'll do like if k equals 0, return head. Else if k is greater than 0. So here now we're going to say k equals length mod k. Right? No, k mod length. K mod length. So we mod by the length. Because again, if we have a k value that is greater than the number of nodes in the linked list, you just mod by the length to get a simpler value. And then what do we do? Well, we want to traverse. So number of nodes to traverse. Const number of nodes to traverse equals to the length of the linked list minus k. Length minus k. This will bring us to like the node that is the new tail. Right? So here the length is 6 minus k 4. We have 4 nodes to traverse, 0, 1, 2, 3, to get to the new tail. 3 is the new tail. Okay? So number of nodes to traverse is this. We are going to say let current node equals head. Okay? And let number of nodes traversed equals 0. Okay. And then we say while number of nodes traversed less than, and here I guess we don't even need to have this variable. Let's just do length minus k inline here. So let me delete this. While number of nodes traversed less than length minus k, you increment. So you do number of nodes traversed plus plus, and then you say current node equals current node dot next. And we don't have to do null checks here because we know that we're going to be like smaller than the length. So that would mean on the head, we're at 0, we increment to 1, and we move on to the next one. So I think we want to start at 1, right? We want to start at 1. Start at 1, immediately increment, and if we're less, and then boom. That way, let's see, here, we would start at 1, immediately increment to 2, here. Then check this, immediately increment to 3, boom, here. Immediately increment to 4, boom, here. And now we're 4, so we stop where current node is 3. We stop before even visiting 3. Yeah. Okay. And so now we can say the current node is our new tail, right? The current node is our new tail, and our new head is going to be our new head is going to be the next node. So we can say, I guess we should have a new head at the top, like let new head equals head, and we can say new head equals current node dot next, and then we can say current node dot next equals null, because that's our new tail. And then we can just say get the tail of the linked list and set it to point to the previous head, right? And then finally here we return new head. Okay, so then to get the tail, we could just keep iterating, but I think it's going to be easier if we just do a function called, because these are all like O-then operation, linear operations, so we don't really care to have like a bunch of different functions. So let's just say get list tail head. This is going to be very similar to this. Whoops, it's just going to be let current node equal head. We don't need the length. While current node node dot next. So while current node dot next, and we know that head is never null, so we don't need to handle like where head is null. While current node not next is not equal to null, just current node equals current node dot next, and then we return current node. So this gets us the tail, and we can just we can grab the tail right here. So we can say const tail equals get list tail head. Then length, we have the list length. We have the new head, which starts out as the head. Let's see, just for k equals 0, let's see if we can just handle this here. 0 mod length would be 0. Let's just keep this for now. Let's just keep this for now and return the new head. Or no, actually, let's just do this. Look, we'll do if k greater than or equal to 0, else if k less than or equal to 0, handle negatives, and then we just return new head. If k had been equal to 0, then new head would still be the head. Okay, so current node dot next equals null. We've set the new tail, and then we can just say tail dot next equals head, the original head, right? And that's it. We're done. Okay, so and we've set the new head. We've set the new head, so we are done. So that handles positive numbers. Now, what about negative numbers? So negative numbers, let's see. So let's see if k is equal to negative 2, right? So if k is equal to negative 2, then the where is the new head if k is equal to negative 2? The new head is from the start, right? So here, sorry, k is equal to 2, so the new head was 4. K is equal to negative 2, so the new head is going to be like 2 from the head. Okay. So then that's actually very easy. It's just literally the number. It's like this number of nodes traversed, like length minus k here. It's actually just k. The number of nodes to traverse, right? Yeah. Okay, so actually that's very easy. We can just do this. Look. We can say let number of nodes to traverse, to get to the new tail, or actually we can just do this. Look, let new tail position. That's a much better variable name. Let new tail position equals new tail index, I guess. New tail IDX equals length minus k, right? Length minus k. And we can say if k is negative, if k less than or equal to 0, then its absolute value of k. Or sorry, then new tail IDX is absolute value of k. Yeah, it's not length minus k. It's equal to, how do you do absolute value in JavaScript? Absolute value, I think. Or let's just do negative k. Equals negative k. Yeah. So negative k. Can you do this in JavaScript? You can do negative variable? Yeah, right? You can do like k multiplied by -1. Let's just do that for now. Okay, and then we don't need to handle this. Then we can just literally we don't need to handle negatives. Then we just, boom, this is the block that does it. So k equals k mod length. I guess this should actually go above here, right? And then new tail IDX equals this. If k blah blah, current node, and then you do the exact same thing. You literally do the exact same thing. Okay, so I think this works. Let's go through an example just so that we don't get confused. And then we'll try submitting this. So I guess without going through an example, right now I'm at 17 minutes. So it's funny, by the way, this problem took, let me pause. This problem took much longer, I feel like, than river sizes from a point of view of getting the solution. River sizes felt like it was just longer to code out, but I feel like I immediately knew how to solve it. This was way trickier in my opinion, which is why this is a hard problem and not a medium one. Okay, resume. So, okay, let's go through an example. So imagine we have these examples: 0, 1, 2, 3, 4, 5. And we have k equals 2, and then we'll go through an example where we have k equals -2, okay? So with k equals 2, the solution is 4, 5, 0, 1, 2, 3, right? That is the solution. Yeah, 4, 5, 0, 1, 2, 3. Okay, so that's with k equals 2. So here we first start by saying our new head is our current head. So that's 0. The tail is getListTail. And getListTail, we just do current node equals head. So far as the current node doesn't have .next isn't null, so it's not pointing to null, we keep moving the current node to the next node. And once we have that next node being null, we return a current node. So this returns the tail. And this is an O of n operation. We go all the way to the end of the linked list. So the tail here is going to be 5. Length, getListLength, same thing. So long as the current node is not null, we keep going to the next node and we increment the length. immediately. So we would immediately increment the length to 1 on the head and go to the next node, blah, 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 all the way till the end. Okay, another O of n operation. So we're at O of 2n so far. So just remove the 2. That's the length. Then k equals k mod length. So that speaks for itself. I hope that negative numbers can mod and retain their negative. I believe they do in JavaScript. I think it might be a tiny bit different in some languages, but we're going to stick to that here. This is because you just don't need the k to be, the absolute value of k to be bigger than the length of the linked list. So, because it just like is going to redo like a bunch of loops, right? So the new tail IDX, which assumes that k is positive, is length minus k, okay? Length minus k. The reason it's length minus k is because here we've got length 6, k is equal to 2, so 6 minus 2 is 1, 2. So it's this node, that's 4, 0, 1, 2, 3, 4. So I guess position. We shouldn't call this IDX. IDX implies like 0 index. Let's do new tail position. Pause. And here, instead of length minus k, I had a typo. This should be new tail position, okay? New tail position. So, new tail position, okay, is 6 minus 2, so 4, which is this. If k is negative, then the new tail IDX is not length minus k. It's like k nodes from the start. So it's the absolute value of k, okay? So k, we know that this is negative, k times minus 1. And so here, k would be 2, k times, or k would be negative 2, because I guess, yeah, if this were k equals negative 2, then the solution would be 0, 1, 2, 3, 4, or sorry, what am I talking about? It would be 2, right? It would be 2, 3, 4, 5, 0, 1. And so the new tail IDX is this node 1, which is at position 2, okay? Negative 2 times negative 1. Okay, that's the new tail. Then we do current node equals head. The number of nodes we've traversed so far is 1, because we're already at the tail, or sorry, at the head. So long as the number of nodes traversed is less than the new tail position, then we do stuff. So number of nodes traversed plus plus, and then current node equals current node.next. So here, in the case of negative 2, where k is equal to 2 now, we would move on to the second node, 3, and we would immediately have number of nodes traversed equals 2. So 2 would no longer be less than the new tail position, which would be 2, so we would be done. Otherwise, with the positive number, we would have 2, then 3, and then 4. We would be done here, right? And I guess we would increment to 4 at the end of node 2 here, node with value 2. And so at that point, we're done. We're at the new tail, okay? And so we do new head is the next node, so current node.next, and current node.next is equal to null. This makes it the new tail by having it point to null. And finally, we grab the tail. We grab the tail of the linked list, which we had at the beginning, and we do tail.next equals the original head, because you always loop it back. Okay? And that's it. That is it. And then return new head. And I believe this will handle, so I think this works. I think this all works. And by the way, this is all like a O of n algorithm, right? Or not even, it's like O of new tail position algorithm, the rest of the function, but total O of n. I believe that this will work if this will work for like k equals 0 or for length equals 1, But just to be clear, to be safe, I'm going to handle these two edge cases, and then we'll see afterwards if I remove the handling, if it still works. So we're just going to do if k equals 0, return head. If length equals 1, return head. Just for to see. Okay, so I think this works. Let's hope that it works. Ready? It doesn't work. Okay, so it doesn't work. Since I am running out of time and I don't want this to go too much over time, I'm just gonna run code to see like if I have just a typo or something, and then we'll go into it. So 9 tests out of 20 pass. So let's see. All the last ones fail, and 7. So 7 is when 0, 1, 2, 3, 4, 5. And k is equal to... Wait, what's the... K is equal to 6. Oh, I think... Okay, so I think what's happening here is 6 is the length. Okay, so I think the k equals 0 isn't being handled properly. Let me move this down here. So let me move this under the k mod length. Because 6 mod length, 6 mod 6 is 0, right? And that one was failing. So I think that the 0 wasn't being handled by the rest. So let's just run code again, or I guess submit code, still failing. Run code. Yeah, so 7 now is passing. 7 is passing. And then, okay, so a few others are passing. So let's see. Cannot read property null. Huh. Null. Okay, so these are all errors. And these are all where k is negative. So I'm not handling the negatives properly. So let's see. If k... Oh, because I had new tail IDX. Look, I have typo. Okay, so this is a dumb typo. I had new tail IDX instead of new tail position. So new tail position. Okay, so I think this will work now. Please, please, please. Yep. Okay, it works. Awesome. So, okay, so that it wasn't like an algorithm issue. So that was a typo. And let's see if I remove this. Let's see if it works. No. Okay, so the k equals 0 is not handled with this code, which probably makes sense. Let's see if length equals 1 is handled. So length equals 1 is handled, meaning here, yeah, if the length is equal to 1, it doesn't matter. So I'm going to remove this. To be honest, I don't really want to see why k equals 0 is not handled. It should be pretty easy, right? Length minus k... Oh, because here, I'm too lazy to see why k equals 0 is not handled here. But anyway, this is pretty clean. And to be honest, I should even move this. Or no, I can't move it up because we have to mod first. But okay, I think this is fine. I'm gonna call it here. I'm kind of like burnt out from algorithms. I'm glad I got it. I guess let me pause. Roughly 27 minutes with this one, and it wasn't on the first shot. I had this handling needed to be under the modding, not above it, and I had a typo. But overall, I'm pretty satisfied with the performance on this problem. I would say, like, you know, if I had to judge myself, I would say this is like, I would give myself a higher on this, maybe even a strong higher, because why not? And also in an interview, I wouldn't have said all this mumbo jumbo about like handling k equals 0. I would have just handled it. No questions asked, you know, no need to like confuse the interviewer. 27 minutes, 21 minutes, that's basically 50 minutes. And then 5 minutes, that's like 55 minutes for easy, medium, hard. I'll take it. With that, I really hope that you enjoyed this video. Don't forget to smash the like button if you did. Subscribe to the channel if you haven't already. Let me know what you thought about my performance in the comments below. Do you think you would have done better? Do you think I even did well? Do you think I did poorly? Let me know. Follow me on LinkedIn and Twitter if you enjoy short form written content, Instagram if you like pictures, and I will see you in the next video.